thank you for the opportunity to give my talk. And my talk today will be about Cameron-Liebler sets of k-spaces in PG and Q, and in particularly about non-existence results of these Cameron-Liebler sets of k-spaces. And this is in fact joint work with Jan de Beule and Leo Storme. So this is a small summary about what we're going to do today, but I suppose we are really getting into it now. So first, some motivation why this talk fits inside a seminar about cryptography and coding theory. If we consider the finite field FQ and we look at the productive space PG and Q, then we can see that there are linear codes, the traditional codes, like where the code words are in fact the vectors of PG and Q, and we have the Hamming distance as the distance function. And we can also look at subspace codes, where the code words are in fact the subspaces of PG and Q. And one possibility for a distance function is a function that is denoted here below. In these subspaces codes, it's very interesting to look at certain properties and certain subspaces. So in general, it's very useful to study subspaces in PG and Q. So let us get to the main topic. And before I can define Cameron-Liebler sets of k-spaces, I will need the point k-space incidence matrix of PG and Q, which is a 0-1 valued matrix where the points are indexing, the rows are indexed by the points and the columns are indexed by the k-spaces. And we put a 1 at position ij if point I is incident with k-space j and a 0 elsewhere. Using this point k-space incidence matrix, we are able to define a set of k-spaces, which we will call Cameron-Liebler sets of k-spaces, or CLKS for short. And it's in fact a set of k-spaces such as its characteristic vector lies inside the image of the transpose of that point k-space incidence vector. In fact, it means that this characteristic vector is a linear combination of the point pencils, where point pencils are all the k-spaces through a fixed point. This set L has a certain parameter between those two values, and this parameter is depending on the size of L. So we have that Gaussian coefficient that denotes all k-1 spaces inside PGn-1Q, and we have x times this Gaussian coefficient. An equivalent terminology is in literature, they often use Boolean degree 1 functions instead of these Cameron-Liebler sets. And the Boolean function is derived from the fact that the characteristic vector is a 0-1 valued function. And the degree 1 is denoted due to the fact that it's a linear combination of point pencils. So let us give some trivial examples, and I'm denoting without complements because in fact a complement of a Cameron-Liebler set is also a Cameron-Liebler set. We will get more into that later. But the trivial example for x equals to 0 is the empty space, the empty set, in fact. And yeah, that's the only possibility for Cameron-Liebler sets in x equals to 0. For x equals to 1, we can choose all k-spaces through a fixed point P. For this value of x, we can consider all k-spaces inside a fixed hyperplane. And we can take the disjoint union of two previous examples to get a new example, where the parameter is the sum of those parameters of these two examples. And we can consider all k-spaces inside a fixed hyperplane or through a fixed point where the point is not inside the hyperplane, such as the figure here. Yes. A question we could ask are there any other examples? And that's a very hard question. And one of the methods that people try to solve this question is by trying to prove the negation. Are there any parameters x where we are definitely sure that there aren't examples to find? And that's something what has been done previously by other sources, like this theorem, which is kind of the first trivial version. Like for x equals to 0, we have only the empty sets, which is of course a kind of trivial. For x, for a Cameron-Liebler set, we know that x cannot be between 0 and 1. And if n is big enough, like bigger than 3k plus 2, we have that x cannot lie in this interval. Also, for x equal to 1 and n big enough, we have a classification for the parameter x equals to 1, which tells us in fact that it could only be a point pencil. The more interesting results about this non-existent condition is the following from the same article. Here they prove for n bigger or equal 3k plus 2 that there does not exist Cameron-Liebler sets of k-spaces for x in this range. This is a very beautiful result, and it's often improved by a theorem from an article from Ferdinand Irringer, where he often improves this interval, where he often improves the upper bound. But to make things easier, I have the following conclusion, where for sufficiently large n, we know that for the parameter x smaller than 2, we only have the trivial example like the empty set and the point pencil. For x bigger or equal than 2, we have in the best case scenario, and this is in fact a combination of these two theorems in the previous slides. We have in the best case scenario a non-existence till the q to the n minus 2k divided by 3. So x should be bigger than this size. I say that this is the best case scenario because it's often much worse than this. But but if we improve this bound, we in fact have a new result, and that's what we are going to do today. So our goal is to improve this upper bound. And before we get started to that problem, I want to give a final remark, and that's what I already briefly mentioned. Like the complement of a Cameron-Liebler set of k-spaces of a certain parameter x is in fact a Cameron-Liebler set of k-spaces of parameter the maximal size, the maximal parameter minus x. This means that a classification for all parameters that are smaller or equal to the first half of this interval yields a classification also for the complementary parameters and yields a full classification. So we should put these results in this perspective too. So now we're going to try to find to improve that upper bound that we have seen in this previous theorem, and we're going to do that by looking at subspaces. And this result is kind of folklore, and it's also beautiful at the same time. So if I have a Cameron-Liebler set of k-spaces with n big enough and bigger or equal to 2k plus 1, and I look at a certain subspace of a certain dimension that is bigger or equal than k plus 1, then I know that LP, which consists of all k-spaces inside L and inside that subspace, is also a Cameron-Liebler set of k-spaces inside P. So by looking at a subspace and looking at all the elements of L inside that subspace, we in fact obtain a Cameron-Liebler set too. One important remark is that I did not mention the parameter. It could be that the parameter changes, but that's something where we don't know anything about. The proof of this theorem is actually quite easy. We have our points k-space incidence matrix. We order the points and the k-spaces in such a way that we first see all the points of P, all the k-spaces of P, and I know that my Pn is of this form. So where Pp is in fact the point k-space incidence matrix of the subspace P. These are unknown parts that we are not interested in, and this is a zero matrix due to the fact that points outside of P cannot be incident with k-spaces inside of P. We know that L is a Cameron-Liebler set, so L lies in the image of this matrix, so there exists a V1, V2 for which this holds. And if I calculate this, I get this vector, and all the sets of k-spaces inside P are just the first number of k-spaces inside this KL, where this in fact holds. So we in fact have that the restriction to P, that vector lies inside the image of this matrix, which is by definition a Cameron-Liebler set. So we have a Cameron-Liebler set by looking at the restriction. Very nice result. And by looking at these subspaces, I want to give first of all the main strategy, how we're going to improve that bounds, and that we're of course going to do by looking at these subspaces. So if L is a Cameron-Liebler set of k-space in PG and Q of a certain parameter x, then the first step we want to take is we are picking a k-space inside L. I should remark that we are here using that L is not empty, so that's something we should assume in the next slide. And we look at all 3k plus 2 dimensional subspaces Pi through k. We know that for every pi, the set LPI, which consists of all k-spaces inside L and inside pi, is a Cameron-Liebler set of a certain parameter, xpi, but this parameter we don't know anything about it. It's just a notation. The reason why we choose this dimension is due to the fact that this is the smallest possible dimension where we can make this story work, and it will give the best bound. So we could fill in a 3k plus 4 or etc. or 3k plus 3, but it will also always receive, it will also end in a bound that is worse than using 3k plus 2. Step 2, we will find a relation between the parameter x and xpi, and that we will do with a double counting. Step 3, we were looking at results of xpi in regard to x. So we're going to try to find some results for xpi and try to obtain a result for x. And step 4 is actually combining all this stuff above. So let us first, excuse me, take a look for step 1. Step 1, I suppose that L is not the empty set, and I fix a k-space k inside L. And I look at all 3k plus 2 dimensional subspaces through that space k. We have P1, P2, Pi, etc. L restricted to all these subspaces define Cameron-Liebler sets of a certain parameter xpi. That's in fact step 1. Step 2 is to find a relation between this xpi and this parameter x. And we will do this by a double counting of the pairs TP, where in fact we have a 3k plus 2 space through our chosen subspace k, that of course lies in L, and our T will be an element also lying in the subspace in the Cameron-Liebler set, and also lying in P that is disjoint to K. And this is a number that we can actually calculate due to the fact that the number of skew k-spaces inside L to a fixed k-space k is a constant that is solely depending on the parameter of the Cameron-Liebler set. And so we have in our double counting a part where we use the parameter xp, the parameter of the corresponding plane of the corresponding 3k plus 2 space, and a part where we use the parameter x. And due to the lack of time, I will give you the result of this double counting, and this is in fact this equation here. Here the sum goes over all pi, all 3k plus 2 spaces through the fixed k space k, so the sum of all these parameters. KL of k is of course always 1 because k lies inside the Cameron-Liebler set, and this is the characteristic factor, but due to generality, I have put it like this. So the following step, step 3, what holds for xpi? So the first result is something that you have already seen in this presentation, is that for Cameron-Liebler sets, we have that x cannot lie between 0 and 1, and if n is bigger or equal than 3k plus 2, then x cannot lie between 1 and 2. And this is exactly the reason why we are using these 3k plus 2 dimensional subspace in order to use this theorem. The second part we will get later into it, but the important part here is that we know that for every subspace pi, we have automatically a subspace k inside of pi inside L. So L pi can never be empty, so xpi can never be 0. Xpi, it should be xpi, can never be 0 or 1 or 1 and 2. But the only question we are asking if xpi can be 1. In that case, we know that LPI is a point pencil due to part 2, but that, of course, could happen. And the next slide will exclude this xpi. And this is, in fact, a result that is a generalization from the results of in the thesis of Drudge, where he found this for a k equals to 1, and we are able to generalize it for general k. And it says that if we look at an e-dimensional subspace P, and we see that L restricted to that subspace, so all the k spaces inside L inside that subspace is a point pencil, then we have that L is a point pencil in PG and Q. This in fact means that if one of the xpi is 1, then we have a point pencil in one of the subspaces, then x should also be 1 because L is a point pencil. So the negation of this is that if L is not a point pencil, then we have that xpi cannot be 1. So let us conclude that in the previous statement, xpi cannot be 0, cannot be like between 0 and 1, 1 and 2, and also cannot be 1. So our conclusion here is as if we have a Cameron-Liebler set of k-spaces of a certain parameter x, or in PG and Q for n bigger or equal 3k plus 2, 3k plus 3. The reason why this holds is due to the fact that we need to have 3k plus 2 spaces. And we have that L is not the empty set nor a point pencil, so x cannot be 1. Then we have that, first of all, step 2, this equation holds. For xpi step 3, we have that x cannot be 0, xpi can never be 0, xpi is bigger or equal to 1. That's that theorem. xpi cannot be 1 due to the fact that we have excluded the point pencil that L could not be a point pencil. xpi is bigger or equal than 2 due to that theorem again. And then if we fill in xpi bigger or equal than 2, then we get this upper bound, which is in fact roughly of size q to the n minus 3k minus 2, which is kind of pessimistic, but it's vaguely the same. So this means that that for these cases we have that x should be smaller than 2, so it should be 0 or 1, or x should be bigger than this bound, which is in fact an improvement if n is bigger than 4k plus 4. So this is quite a nice result. I want to end with telling you that there is also an affine version, like where a Cameron-Liebler set of k-spaces in AG and Q is defined similarly, like also inside the image of the transpose of the point K incidence matrix, and we have a similar result that is also better than the existing bound. This is for all values of n where it holds for. Here, one remark is that it's bigger or equal than 2k plus 2, not 3k plus 2. So these are the theorems that we have found. I've more listed them above each other, and I want to thank you for the attention. And if there are any questions, I think we have a few minutes left, or I'll be in the chat afterwards, or you can send me an email.
Thank you, Jonathan. I don't know if there are some questions. You can also put on the chat or by email, as Jonathan supposed. I just a quick question. So at the end, it's some hope for some classification results or
well, yeah,
for some key sets in AG and Q or not?
Yes, a classification would be very beautiful. Finding these examples are hard, and there are also people who are speculating that, for example, these examples do not exist. So this could be a first step into that direction.
Okay.
But in order to give a speculation if they exist or not, it's really hard, because in the case of k equals to 1. And n equals to 3. It was also speculated at a certain time that there weren't examples, and suddenly they found an example. So perhaps similar miracle can appear here. But yeah, it's definitely, yeah. It would be very nice to have a classification or a general non-existent result.